For today's level up problem, we have a problem from 1985 AIME. It is number 13. That means it is one of the more harder questions on that 15 question test. The problem is, the sequence a sub n is given by a sub n equals 100 plus n squared for n equals 1, 2, 3, etc. For each n, let d sub n be the greatest common divisor of a sub n and a n sub 1. Find the max value of d and n for positive integers n. Obviously this is slightly altered for ease of explanation, but the problem is generally the same. Let's have a look at this. If we have d sub 1, that's the greatest common divisor of a sub 1 and a sub 2. So if you look at a sub 1, that's 100 plus, that's 1 squared is 1. So we have d sub n equals the greatest common divisor of 101. And if we have a sub 2, it's 100 plus 2 squared, that's 4, so it'll be 104. Sorry, that's d sub 1. If we have d sub 2, then we have the GCD of 104 and 109. Okay, we see where this is going, but we can't sit there and find GCD for every number for all infinite time. So we need to find a better way. We need to generalize it a little bit. And so where we'll use a sub n and a n sub n minus n plus 1. So we know in general d of n is going to be the GCD of a sub n and a sub n plus 1. And I'm going to flip them around so that the larger one is on the left. And then we can use their definitions to say GCD of n plus 1, a sub n plus 1 is going to be 100 plus n plus 1 squared. It's pretty straightforward, and a sub n, straightforward, it's right up there, 100 plus n squared. Great. And we'll go ahead and expand the n plus 1. That's n squared plus 2n plus 1. So we have the GCD of n squared plus 2n plus 100 plus 1 makes 101. And we have the n squared plus 100 over here. Now we'll start looking at using the Euclidean algorithm. Just to recap, by the Euclidean algorithm, you have the GCD of A and B. Then you can take where B is smaller, you can slide the smaller number over, yes, make the difference, subtract, and you get A and B is the GCD of B and A minus B. Now, you can subtract this as many times as you want. Repeated subtraction is essentially the same as division, and you're finding the remainder. So you can actually make this shortcut and say B and the remainder when you divide A and B. That's what mod means. Example 15 mod 2. And 15 divided by 2 gives you 7, but with a remainder of 1. So that actually equals 1, and we want the remainder when you keep subtracting. But we do not need to use this for now, as we have this to do. So we'll take the smaller number, which is obviously n squared plus 100, and we're going to slide it to the left, and we'll take the difference, n squared minus n squared, that goes away, 2n plus minus 0n, that's 2n, and we have 101, and 100, that's just 1. Great. We still have n's, and we want to try to get rid of them. So we'll see if we can do anything else with them. Obviously, this n squared plus 100 will probably be bigger than 2n plus 1. Let's see if we can do Euclidean algorithm again. Here, let's try the division method. N squared plus 100 divided by 2n plus 1. Polynomial, long division. It works the same way. How many times does 2n go into n squared? Let's half an n, because 1/2 times 2 makes 1, and n times n makes n squared. 1/2 n plus 1, or times 1, that gives you 1/2 n. Then you can subtract those, and you have a negative 1/2 n plus 100. How many times does 2n go into minus half of an n? It's negative a fourth. We have fractions. It's not looking so great. But let's keep going. Minus 1/4 times 2n gives you the minus 1/2 we need. And minus 1/4 times 1 gives you minus 1/4. You subtract those and you get the remainder is 99 3/4. So obviously something went wrong, and we cannot do this. But what can we do instead? Well, this is part of where the difficulty of this problem comes from. It's realizing this number is odd, because you have even number plus 1. So this number is odd. So it will never have 2 as a divisor. It can never be divisible by 2. Now what does that mean? The greatest common divisor is also never going to be a multiple of 2. The greatest common divisor is odd. You know, this is odd now. But because this thing is odd, if we multiply this thing by an even number, then the GCD won't change, because this is still odd. So let's give this a try. We'll multiply this by 2 and see what happens. GCD of 2n squared plus 200 and 2n plus 1. So what did we just do? This contains some odd divisor, and that's why it's the greatest. There's a greatest common divisor, and it's odd. This contains some odd divisor. This contains the same odd divisor, and probably other stuff, but it also contains a times 2. But the times 2 isn't odd, which means the times 2 is not in here. And so this is still actually the same greatest common divisor. But what does that do for us? Now we have a 2n and a 2n squared. So when we go to long divide, we can say 2n goes into 2n squared n times. We have a whole number of n's. That's hopefully going to lead us in the right direction. We subtract, and we have a negative n plus 200. So this is our remainder. It's probably going to be smaller than this. So we can say GCD of 2n plus 1 and negative n plus 200. Alright, then let's divide this and see what happens. If we divide 2n plus 1 by minus n plus 200, then minus n goes into 2n negative 2 times. Negative 2 times minus n, that's 2n. Negative 2 times 200, that's minus 400. And we can subtract those. 2n minus 2n is 0. 1 minus negative 400 gets you positive 401. So in other words, we can take the smaller number, minus n plus 200, and a 401. Now, in order for it to be the biggest, greatest common divisor, d sub n, we want this to be 401 and this to be 401, so that the GCD will be 401. That would be ideal. Let's see if that comes true. Minus n plus 200 equals 401. And what do we get? If we add n to both sides and we subtract 401 on both sides, we get that n is minus 201. But if you go back to the problem, remember that n can only be positive. N equals 1, 2, 3. So this clearly didn't work. N cannot be negative 201. But let's see if we can go back and say GCD 2n plus 1 and 401 is still dn, because all of these share the same GCD. So what if we set 2n plus 1 equal to 401? Well, then we get n equals 200. And we see why this case didn't work, because this is 0. So we actually had 0 and 401. So n equals 200 is a positive integer, and this works. So our final answer is the GCD, greatest common divisor, is 401 is the biggest. Now this was a very complicated use of Euclidean algorithm, but it shows how useful it can be when you have greatest common divisor problems. Furthermore, we saw here that this is 0 and 401, so we know now that the greatest common divisor between 0 and some number is that number itself. And that makes a lot of sense. If you have GCD of A and A, that's obviously going to be A. They both share A. But if you apply the Euclidean algorithm, we take the smaller number, they're both the same so it doesn't matter, A, and we take their difference, 0, and that should still be A. So that's a very useful thing to note as well. If you can find a 0 in the GCD, or you can make a 0, then that will tell you that the other number just is your GCD.